Thank you, Nick. I probably should have shortened his bio, but thank you. And yeah, I go by Hussein, and I'm really happy to be invited to participate in this panel. Excuse me. So usually, yeah, I'm participating, as partly as NSF and partly as just me. So opinions are just my opinions. But it's always good for NSF program directors to reach out and do outreach to the community and listen to various ideas and feedback. So I look forward to what the panelists will say and what the other audience members will also contribute to this panel. I'd like to introduce, maybe start by introducing the panelists, and then I will pose some questions that we will sort of try to talk with respect to. And I do have some slides, and I know we're starting a little bit behind in time. So I will try to make them brief, but I always try to not miss an opportunity to talk about opportunities, research opportunities at NSF for the different for the future research. So so let me start by maybe I'll follow Nick's guidance, and I will introduce people, but I think that's I'll just go ahead and do that. So let's see, Professor Kong Shen is one of the panelists. I have them here organized in no particular order. So Professor Shen is currently assistant professor in the Electrical and Computer Engineering Department at the University of Virginia. He received the PhD degree from the Electrical Engineering Department at the University of California in Los Angeles. And his general research interests are in the area of machine learning and wireless communications. And I apologize ahead of time if I kind of shorten the introductions a little bit, just so that we can save a little bit of time. But I will mention that he received his NSF Career Award in 2022. Congratulations. And Best Paper Award from IEEE ICC in 2021. He serves as associate editor for several IEEE journals. I'm not going to list all of them. And he's also a member of Spectrum X in the NSF Spectrum Innovation Center, which I'm going to talk about briefly today. So thanks, Kong, for being on this panel. Next is Professor Randall Berry. Professor Berry is the chair of the Department of Electrical and Computer Engineering at Northwestern University, where he's also the John Dever Professor. And his research interests span topics in wireless communications, including spectrum sharing, network economics, and information theory. And he received his PhD from MIT in 2000. And he's an IEEE fellow, recipient of an NSF Career Award. And I guess you now remove the year, because it's no need to mention the years anymore. And of course, with his collaborators, you're always careful to point out that this is with his collaborators and acknowledges his collaborators. He received several Best Paper Awards. So thanks, Randy, for serving on this panel. And next is Professor Dimitris Pados. He received the diploma degree in computer science and engineering from the University of Patras in Greece, and the PhD in electrical engineering from University of Virginia. And he majored in communications theory, systems, minor in computer science, and math, and so on. He was a professor at University of New York at Buffalo. So I thought I mentioned that piece because this is our host. And he was there from 1997 to 2017. He was assistant, associate, and then full professor there, and a chair professor as well. And then in 2017, he moved to Florida Atlantic University as the Schmidt Eminent Scholar, Professor of Engineering and Computer Science, and a fellow of the Institute for Sensing and Embedded Network Systems Engineering. He also, at Florida Atlantic, he founded the Center for Connected Autonomy and AI. And he's currently acting executive director of iSense, which is a university-wide engineering research center. He has served as a PI in many grants on NSF and DoD, and published extensively in predominantly IEEE venues, and also received many best paper awards and so on. So I'll maybe stop here. And thank you, Dimitris, for being on this panel. And last and not least, Professor Mohammed Kurum. He received his Bachelor's of Science in Electrical and Electronics Engineering from Bogazici University in Turkey, and MS and PhD degrees in Electrical Engineering from George Washington University in Washington, DC. He's currently an associate professor and Paul Jacob Endowed Chair in Electrical and Computer Engineering with Mississippi State University. He's the co-director of Information Processing and Sensing Lab, and his current focus is on recycling the radio spectrum to address the challenges of decreasing radio spectrum space for science while exploring new microwave regions for land remote sensing. Dr. Khurram is also a senior member of IEEE Geoscience and Remote Sensing Society, and a member of the U.S. National Committee for the International Union of Radio Science. He served as an editor for several IEEE journals. He received several awards. It's a long list, and including Career Award in 2021 from NSF. So I'll just stop there and thank Mehmet for joining. I ask your permission to call on first name basis just to kind of make it easier to have a discussion. So thanks everyone. I think I'm not missing anyone. So I wanted to start by maybe sharing some slides, and I'm going to try and be brief. So maybe to some extent too fast, but feel free to stop me anytime. So this panel is about next frontier or in active passive spectrum coexistence, which has been a topic of interest and a topic of funding from NSF, particularly through the SWIFT program, but through many other programs. Spectrum X Center also focuses on that. So I just wanted to give a quick overview of some highlights at NSF related to this. And I promise I won't take too much time. I've broken that promise in the past, so just a heads up. So do stop me if I'm Nick, if I'm like running out of time. You kind of tell me, and I will ask the panelists to also give a brief 3-minute perspective on the panel questions that I'll post at the end of this presentation, just to get the discussion going. Also I'll try to keep everyone to a brief few minutes. So of course, many of you know NSF. NSF funds like 75% of federal funding to computer science departments, about actually 80% at least, and about 70-something% for engineering. So many of you know the NSF and its directorates. The directorates are somewhat organized similar to a university in terms of the schools. And then within the directorates, there are divisions which are similar to the departments. So if we look at advanced wireless research, there are multiple dimensions and aspects. There is hardware and there is software. There are data sets which are becoming very important to do any kind of machine learning research or data-driven research. There are the communications and computing aspects of networks. And there is, of course, AI and machine learning and other tools that are emerging. And then there's the spectrum as a resource. And so the spectrum sort of interacts with all of these questions. And then, of course, platforms for research in order to generate some data sets or test coexistence or validate concepts, theoretically driven concepts. So, so many of you know these directorates. There are 7 science and engineering directorates, and there are 3 interdisciplinary offices. And I just wanted to mention something about this new office here, this 3rd office, technology, innovation, and partnership, because it's new. Even though I'm not there, I'm in this yellow highlighted directorate, which is size. But TIPS or TIP is a new directorate, technology, innovation, and partnership. So I wanted to just mention something quick about it. It's just been established. Some of these names might be familiar to you before. Definitely Thiaga was a program director, was exactly in my position years ago. And he's now a division director in TIP. And many of you might know also Erwin from his role before in the front office in size. So what does TIP do? And what is different about it? It's about translational research, and there is this kind of classification or dichotomy of different kinds of research that has existed throughout, humanity, in terms of basic versus translational. And this is how use-inspired research, which is now a new kind of buzzword, if you like, or favorite word, just like transformative research that we're very fond of. There is now this translational research and use-inspired research. So I ask you to maybe check what it means. So it's research not to proof of concept of an idea, but more a use-inspired, as in the use itself generates key new basic research questions. And so TIP is actually going to be working with all the directorates, and you'll start seeing solicitations that are sort of rooted in different concepts or domains, like engineering versus science, but they all have a translational dimension. And you must have seen a lot of Convergence Accelerator awards. Now SBIR and STTR are existing programs, but now they move to be part of TIP. And there are many other programs. You'll see a lot of programs because this is a new directorate and they need to spend their money. So they're going to create a lot of new vehicles and exciting opportunities for the community. So the basic mission of that directorate is to bridge this gap between basic research that from public funds and private funds for taking ideas to make companies around it. Sometimes the distance is too wide, and TIP is there to kind of ramp up that value and bridge that value. Okay, so I just wanted to mention that quickly so you kind of know what's happening, because it's a big deal. It's an additional $1 billion. And you'll see if the previous budget for NSF was around 7, now it's around 8. And it's because of this. It's additional funds. It did not eat up from existing activities. And actually, there was discussion to even create a new organization separate from NSF. And ultimately, they decided that this would be part of NSF. So any questions? Stop me. So with that in mind, I wanted to talk about also some of the activities and many of the projects or the papers that you've seen today are funded through some of these programs. Advanced wireless research is not one directorate or division, it's an area. So there are many programs that fund projects that overlap with wireless. So that includes the core program, the annual size solicitation, particularly the one in CNS. There's the SWIFT program, which is in collaboration with the engineering directorate. It's a collaboration between SISE and engineering and MPS and IIS, so several directorates. And there are also some one-to-one partnerships like MLWins. There are collaborations that involve funding from industry. If you've seen recently, NSF has been collaborating quite a lot more with industry partnerships. And in those situations, the industry contribute money. So with rings, for example, industry partners each contributed something like 1.5 million. And you had 9 of them. So you had roughly about 20 million extra. And NSF contributed about another 20 million. So you had a 40 million program. And this is all pre-competitive basic research. So the companies, all these results, they share the results with, it's all public. There's just a contribution that they actually basically write a check to NSF, and then NSF runs the competition. So we're seeing more of this, and of course you're familiar with the Power program. There are center skill activities like Spectrum X and AI Edge, which I think some of the presentations today went through a little bit more detail onto those. I think Neshoff was there. He's the Institute Director for AI Edge. And I think there were some members from Spectrum X, including on this panel. So one of the things we're looking to improve is the, working with the community to help make data sets available for AI and ML. And of course, currently many projects have shared data sets. So this is just a sample. NIST has been also publishing and sharing data sets with the community. We're trying to make those easier to find. But also we funded a community research infrastructure, and we consider now data sets as part of the infrastructure. So we're funding a project called RF Data Factory, which today has 31 contributed data sets, 11 APIs that help utilize those data sets, and tutorials and various contributors for varying scenarios that are focused on wireless. Now, SWIFT is a program that ties to the topic of this panel quite closely. It's a collaboration between 4 directorates. There were 3 rounds of this solicitation. There is no 4th round posted, so I can't say if there will be a 4th round or not. But if there is one, there you'll find like there will be a 3 months period where you can get your proposals ready and so on. Similarly for rings, by the way, so rings was a round of funding, and if there is another rings, that we can't say if there will be one or not, but once there is one, you'll find it will be posted for at least 3 months to get your proposals ready. So the proposal, focus has been on effective spectrum utilization, not only between broadband active communication, but also between communication networks and other users of the spectrum. And that has been a very important and active area of research, as we've seen for some of the results of research today. AI institutes is one institute that's funded on related to AI and machine learning to wireless, or in general at the edge. So I invite you to look and collaborate with the team, and you can check their webpage. Spectrum, of course, is never going to go away. So I'm just going to, the concerns about spectrum and the demands on spectrum are only going to increase. And at NSF, there is a Spectrum Innovation Initiative, which is the initiative that funded Spectrum X. It's $70 million per year dedicated for funding that is focused on spectrum. So for some of that, part of that funds SWIFT, part of that funds the Spectrum X Center, part of that will fund other things in the future. And NSF coordinates very closely with FCC and NTIA on those awards as well. Okay, so I'll skip this one, and I'll mention NERDS. NERDS is a additional funding that's available for experimental work on sharing spectrum, and it's about creating safe zones, safe in a win-win way that do not hurt systems that work outside those zones, and also makes the area within the zone sort of protected from interference from the outside, so you can run your experiments and get good results without interference. So there is a first round of NERDS awards. I don't know if they've been announced yet, but they've been decided. I think at the stage where the PIs are told, but the grant is not yet finalized with the divisions of grant and agreement, but this is happening very soon, and there'll be an announcement. Okay, I'll skip that one. And I'll also mention that, of course, the platforms for wireless, advanced wireless experimentation and testing, there's Powder, Cosmos, Airpro, ARA, and then Colosseum joined with supplemental funding from NSF. And almost all of these are active or like available publicly for experimentation, except ARA. The expectation is that it will be available for public access around February, March of 2023. Most of these, all of these websites, they have tutorials about how to use. You can use it for free from anywhere in the world, at least for now, if you are a university. Okay. And of course, we have plans to connect all these together, so some grand plans for the future. So to conclude, I think spectrum and networking, you know, there's this push-pull interaction with society and with companies that create products that change how people go about to use these networks, which again brings it back to science, fundamental science engineering questions. So sharing of spectrum is a tricky challenging problem, and requires a lot of innovation, both on the technology side as well as the policy side. And so we have these questions for the panelists. So this is where I will hand it over to others. So what do you see as the major challenges enabling research on spectrum sharing? So, you know, we did, for example, recently this NERDS Dear Colleague letter, where we try to facilitate research that is especially one that includes experimental research on spectrum. So that's one example. So along those lines, if you could think of what are challenges for enabling research. Now, the other thing is challenges for adoption. So if you have a new innovative idea that could solve real problems, what would be the issue with getting that solution adopted? What do you see as challenges in that path? In your research, in your experience, you know, active and passive systems are sort of multidisciplinary in nature because objectives are very different. So how have you been able to bridge this divide and approach these problems? Of course, you don't have to answer all of these, but if you could answer some or focus on some, it would be great. Now, several, of course, of the projects leverage machine learning and AI. So the question is, are these the right approaches? Are these the effective approaches? Or are we using just machine AI, learning and AI because they're new? But are they the right way to solve coexistent problems? And when would they be the right way? And then last but not least is how could it, how can we promote even more effectively private-public partnerships? Okay, so with that, I'm going to stop sharing my screen, and I'm going to hand this to the panelists. I'm sure they're all eager to give their views about these important questions. So does anyone want to go first, or should we go with alphabetical, or should we go with I hate alphabetical because my first and last name start with an A, so I was always drafted first. So let me go with the same order I presented everyone. So how about, I think Kong was first.
Yeah. Hi, everyone. This is Kong from University of Virginia. For me, I think I can probably pick a couple of these questions that are most relevant to my own research. Like the first one, what do you see as the major challenges for enabling research and spectrum sharing? This is kind of, maybe a coincidence, but spectrum sharing is about sharing with others. And one of the biggest challenges I see is actually how are we going to actually share across communities that we can collaborate together? Because for someone who, like myself, who come from a more of a radio communication background, like today's topic of the passive active, coexistence, I have to admit, I never even thought about this when I was just focusing on communications. I always thought, it's a spectrum. You kind of, you have to kind of coexist with others who are, spectrum users, and they are active transmitters. It's just that, you have to basically learn how to share, how to coexist, so you can maximize the utility. And this is something that until I have to say, in only recent years that I've kind of learned, you have to share the spectrum with other people from different even communities, not even in communications, not even in wireless, some of them may not even be in size. I mean, there are just so many use cases that are related to the spectrum. So it's just, how to broaden kind of the scope that we can kind of work with others and understanding others' concerns, not just our perspective. I think this is one of the challenges that I can see. I don't know if, should I just go on the list of questions? Okay, sure. And another probably is related to this, in my research, I use a lot of machine learning. So this probably is one that I think I can comment. Yeah, machine learning is something that's new and kind of not new, but hot in recent years because of the many successes in different fields. So it is on one hand natural to think of machine learning and try to see if it brings another powerful tool for us to handle the spectrum engineering problems. But on the other hand, some of these tools actually have been considering spectrum engineering. For example, one of my research kind of interests is in the multi-arm bandits. I mean, this has been considered a good tool for spectrum sharing, for many years, and it's not just recently. But the interest and the challenge there, how do you why do you think this is an effective approach? Is because fundamentally, I mean, the underlying problem, really the problem that we want to solve is very much alike. In some cases, it's the same. Although bandits have been developed for other applications, recommender system, for example, but it's a sequential decision-making problem, and there's uncertainty involved in your actions. And many of these key features really are kind of shared by the spectrum sharing and access problems. So that's why I think if you have the underlying problem that is really capturing the key features of the machine learning tool, I think there's a kind of a good place to do research there. And on the other hand, the problem that we are dealing with from a communication or networking perspective would also actually feed back to the research of, for example, of machine learning. I mean, because machine learning itself is a tool, it can be used to solve image problems, can be used to solve computer vision problems, can be used to solve robotics. There are different applications, and these applications obviously have their own features and requirements, and then it's kind of like a loop. They feed back to the research of machine learning, like, we need to improve this, we need to improve that in terms of the machine learning aspect. So I think that part is something that's very interesting to me. I think with that, I'll stop and maybe hand it over to the next panelist. Thank you.
Thank you. So how about I ask, did I present Demetrius first or Randy? Randy.
I think it was me. I'll jump in. Thanks. So I'll pick up on something Kang just said, and I think like the first three questions I see as being very tightly related to each other. I think a lot of the challenges come because it is inherently multidisciplinary. And it is, we have to think about different applications. And as I've, worked with people and talked to people, even the, passive users are not one group, right? I think passive radio astronomy is very different from some of the environmental sensing applications. Some of them are on satellites, some of them are on the ground, right? And they all have kind of different, different constraints. Understanding what those constraints are and how is really important. How long do they have to, integrate over looking at a band of spectrum? Can they, decide, can they shift things in time, or is it really critical to do it at a specific time, right? There's lots of questions like that that I think have to feed into, thinking about sharing, and you really need to talk with domain experts. I'm also from a communications background, so I think that's important. I think another thing on adopting these is with spectrum, it's always, there's a policy angle to it as well, right? You have to, it's not just about technology, but it's about getting things through the FCC and sort of thinking about what's feasible from a policy point of view. And that also often touches on economics. And then on that, I think that's also another interesting thing with the active passive is that, a lot of the passive users are scientific users. And so thinking about, the sort of economic solutions to these problems, it's not quite as clear, right? I mean, they're not necessarily profit motivated in the same way that a wireless carrier is. And I think I'm someone who likes economics, and so I was thinking about are there ways to construct incentives, and what do those incentives look like when you have players that aren't necessarily profit motivated? I think is a really interesting part of this, and again, challenge but interesting. And then I think a final thing it's also with these different communities is there's a lot of I think when you start to talk about sharing between different communities, trust becomes a really big problem, right? The two sides sort of tend to think that one some like scientific users thinks that the cellular people are going to grab all their spectrum, and the cellular people think the scientific users might be being unreasonable in their RFI requirements or something, and trying to establish kind of trust and dialogue. And maybe that also goes to the last question about how to get industry and people interested, is you have to have a platform where you build trust.
Yeah. Great. Thanks. Demetrius, any thoughts?
Thank you, Hussein. First of all, it's great to be with you on this panel. Great to see Randy and Mehmet and Kong, the good old UVA. Thanks to Nick as well for organizing the Buffalo Wireless Day. I guess from what I heard on the radio this morning, it's a good thing that this is a virtual wireless Buffalo Day, right? But I do love Buffalo and UP for sure. I have to say that. So now going through this long list of questions, right, at a rapid pace. As Randy said, sharing spectrum has to do also with space and time, right? So in a way, it might be a good idea to stress at all times that it's basically this space-time frequency continuum that we play with. It doesn't matter what I'm doing down here in Boca Raton, for example, over this band of spectrum, unless I'm doing crazy things, right? And what you guys do up there in Buffalo. So I think it's kind of important if we all focus a little bit in the future toward jointly optimizing, managing, whatever you want to call it, space, time, and frequency. Then I think one really interesting question that I think Hussein you posed was, what's a major challenge, roadblock towards enabling research on spectrum sharing, right? I've been thinking about that, and what really bothers me is this difficulty that I face, and maybe other people face as well, to do controlled field experiments, like truly experiment in a controlled way, and try to play with different interference environments in real life. And I think that in general, wired experimentation doesn't really cut it at the end. You really want at some point to see exactly what's happening between A hertz and B hertz, right? When you put all those signals at the same time up there. And in principle, it can be done. We do it with SDRs, but again, this is something that's very complex and very expensive, actually, honestly, to do it in a school, in an undergrad course or a graduate course, effectively. Another good question that I saw was this one that you posed about challenges to adopt maybe such research in practice. One thing that's kind of interesting with this problem is that dynamic interference avoidance actually requires a closed loop system operation, right? Meaning that the receiver, one way or another, must transmit back to the transmitter some sort of disturbance information that then you may want to use to adjust the levels of transmission. So whenever you have this closed loop type of needs in the industry, commercially, there's always a pushback. It's added cost, right? And actually you're using more spectrum as well to communicate information from the receiver back to the transmitter. And one last thing that I had in mind, and I don't want to take too much of your time, is this concept of passive and active interference, coexistence. Can we think of it? I'm wondering, can we think of it in a unified way, just from a theory point of view? And if you think about it, it's still a transmit-receive problem, right? So when you have an active link, the transmitter sends some stuff to the receiver and you affect others around you, right? When you do passive sensing, again, you have a receiver and what you receive is a very weak, probably, signal from a source that is still a transmitter for the purposes of formulating the problem. But there's a huge difference, as you said there. This so-called transmitted signal from the source is very weak. So it's a low SNR type of scenario there, basically. And that changes everything, of course, right? It's trying to coexist now with another link next to you that works on very, very low SNR numbers, right? But at least, looking at it from this point of view, you can sort of try to unify the theory behind that, and then maybe specialize a little bit toward low SNR detection, protection, and the like. Let me stop right here, and we can take it further later, maybe.
Okay, great. Mohammed?
Hi, everyone. Thank you, Nick, for inviting, and Hussein, thank you for organizing this, and for the panelists and all the attendees, thank you for joining us. Yeah, I mean, the questions are related to each other, and I think the panelists are really touch lots of major challenges already, so I'm just going to echo some of those, and probably I'm going to add a few more. Definitely the biggest challenge is the collaboration, bringing the different disciplines together. That's the big challenge. For example, here, this is the wireless day. Remote sensing community is not here, right? So the people with the wireless spectrums are discussing. And for example, I'm listening, Dimitris, so he's talking about the passive sensing, and maybe the passive sensing is a little bit different if you're from a remote sensing perspective. So for example, there's no really the signals involved. There's no SNR. Everything is N. There's no S, just the N itself, because we're trying to detect the noise as an instance. I think, and the same applies to the remote sensing community as well, because when you go to the remote sensing community, they have really not much idea what's going on in the wireless communication. What are the protocols? What are trying to do? I think there's a big gap between these two communities. So that's a big thing I think we need to resolve. And also, for this problem, the passive users are the victims, right? So they're the one, suffering. So it's a, asymmetric, problem here we're talking about. So it's not the passive is causing the active, but the active, the wireless people are causing the problem to the passive domain. So I think we need to understand that as well. And I want to also add some of the difficulties in terms of, for example, Dimitris, talk about this. test bed, right? We have to have something to test all of this. I think it's very, very important. But one problem with that is the passive is strictly prohibited. So strictly, you cannot transmit anything at all. You cannot get a permission to transmit. So you cannot really do this test in a real environment. So the only thing that you can do is you can do it in an anechoic chamber, in a place that you cannot radiate outside of that, closure, right? So for example, under Swift project, this is exactly what we have in our project. So we're developing an active passive, coexisting test setup, but we can only do it in an anechoic chamber. However, what you can also do is you can perhaps use other bands, like the license band for passive users, and you can transmit your sources for that license band and just develop a radiometer specifically for that band, which is not protected. Might be some other sources available, but you can find out if the source is available, and you can also identify your own sources in that measurements. So that's a possible to do in an environment, in the outside, in the real conditions. You can do that with unprotected part of the spectrum. Also, another problem is when we say passive, I think Barry mentioned about that. There's not just the remote sensing, but there's a radio astronomy community. Right? So it's not one community. But also, when you think about the remote sensing community, there is no single remote sensing community either, because there are people working on the atmosphere itself. Some people working on the ocean. Some people are working on the land, and the requirements are much different. They're not the same requirements. So when you develop something, sometimes you have to develop something very, very specific. So you have to keep that in mind as well. Another point that I want to make is related to AI and machine learning, which is it's a very hot topic. And sometimes for AI and machine learning, we miss the physical context. We just use the black box. So there are lots of domain knowledge and experts are needed if you're really doing this AI and machine learning. And it's inevitable. In some cases, you can't really put a physical frame to the problem that you're dealing with because it's such perhaps very, very complicated scenario that you're dealing with. You cannot define every specific physical contributions analytically, and of course you need to do AI for that. But in any case, I think if you're doing an active passive coexistence, we really need both sides come together and understand the problem. Joint understanding of the problem is needed. I think I'll stop here and maybe I'll continue later.
Okay, thank you. So questions from all the attendees or other people on the meeting. Questions or comments or anything any points that you think could also should also consider in these passive active spectrum sharing.
Hi, it's Nick. Maybe Mehmet can say a little bit about the RFI requirements or tolerance of these devices to
right. That's a good question. If you don't mind, I can share just one slide. Yes. And I can just show you that. Let me prepare here just a second. It will understand a little bit better on that. I mean, this is a topic again. It's a long discussion we can have on this. Let me see. Do you see the screen?
Yes.
Slide? Okay, so let me go over here, one slide. Right, this one. So how small is small? Yeah. For passive micro remote sensing. So that was a question I was posing. We say it is small, but how small it is, right? Just an example. In passive microwave, we have a very simple formula: K, T, B. K is the Boltzmann constant, TB is the brightness temperature, B is the bandwidth. Typically, the brightness temperature is around like a 300 Kelvin. And this is the Boltzmann constant, which is very, very small number. You can see over here, 10 to the minus 23. And then bandwidth, well, I just pick here just 1 megahertz. If you multiply all these numbers, that you can see that the information, the noise that we are trying to detect with a passive system is about 4.1 times 10 to the minus 15 watts, and it is minus 144 dB watt or minus 114 dBm. So you can see how small it is. And this is just getting the entire signal. And sometimes, and most of the case, the requirement for the passive user is, I want to sense my geophysical parameter within a 1 Kelvin, within 0.1 Kelvin, depending on what geophysical parameter you retrieve. And that number gets even smaller if you're trying to resolve 1 Kelvin, accuracy.
Mhm.
So here is an example from an ocean remote sensing. And this is a satellite system looking down to the Earth, about 600 kilometers from the Earth's surface, and trying to estimate the ocean salinity from space using passive microwave radiometry. And the one on the right is showing the dynamic range for that satellite, that mission, which is trying to get the salinity in the open ocean. The salinity varies between 32 PSU to 37 PSU. That corresponds to 2 or 3 Kelvin. So entire dynamic range of this mission is 2-3 Kelvin to detect about a 0.2 PSI sensitivity, the ocean salinity. So if you have anything like 1 Kelvin contribution, it's just gonna say this is a very, very salty, the sea, or it's a very, it's not that salty. And in order to, because like your instrument, you're trying to measure, noise, and your instrument is also producing a noise. And even for that mission, the people are trying to correct the emissions coming from the galaxies, coming from the moon, from the sun and ionosphere. So each one of them is already contributing to your signal, what you're measuring through your antennas. And we're trying to really, correct all of those in order to get this 2 or 3 Kelvin, dynamic range, and so that we get the salinity. But this is a very extreme case. In some cases, not that, stringent, the rules. But just want to give you a feeling about how small is small, for this community. Let me stop sharing here.
Thank you. That's very insightful. Any comments, questions? There is a question, I think. Should I read it? So there is one comment and our question, and it says, I know the USRB is a bit cost prohibitive, but do you think the new USB SDR S like RTL SDR version 3 or Hack RF and others sub $100 SDRs have their place in the research of this kind of I guess I assume it's a question about the passive active. Is there like software defined radio platforms that you can do experiments with for spectrum sharing that are not very costly?
Yes, that's definitely possible.
So it's a good question because actually it's something we do think about when we do community research infrastructure, the availability of platforms to do research on, and including boards and things like that. So, if you do, I think the community has done a little bit of, if you want to do higher frequency research, you'll pay probably tens of thousands of dollars if you're just, or you make your own, and it might not be very smooth in using compared to commercial ones. So it's a valid question in terms of passive active research, given the sensitivities that we're talking about. Are there meaningful, useful SDR platforms that are, I think, I don't know about below 100, but let's say below 1,000. And of course, the question here is below 100. Like, I mean, you can go on Amazon and get some sort of a spectrum analyzer. And depending on the frequency, it will exponentially grow in cost from below 100 to thousands of dollars, right? So, so the question is there enough hardware experimentation at reasonable cost to conduct research for this kind of challenges?
Yeah, I think Hussein, low-cost SDRs can really help, especially if we consider education. But again, these are going to be low bandwidth, right? Small bandwidth type of studies. I mean, we have to clarify that. But that's, for me, is a great first step. If I can have maybe 50 of those $100 SDRs, I can do some really good things over some small bandwidths. And maybe then intelligently I can, infer out of that how things might happen if I operate over, half a gigahertz or anything to that respect, right? But that's a very good question, and I think that's a very promising direction. If we can really have $100 SDRs, that's a step forward in this direction for sure.
Thank you for the question and the answer. Any other comments or questions? Is there another one? No. Okay. So this one is answered. Okay. Thank you.
So, Hussein, if you don't mind, I have a comment or a question. I need some help from Mehmet maybe about this very nice study that he presented. Maybe he can give us a little bit more information about how you approach the sensing problem. Is this sensing that people do directional in any way? Do you have an antenna array system that sort of focuses on a small area of the ocean and gets the reflection back? Is space processing a big part of this effort? It would be great if you can share with us your experience with this type of work.
Yeah, usually, for remote sensing, the resolution is the big thing, right? You want to have as high resolution as possible if you are trying to, resolve some geophysical parameters that you want to estimate. For radiometers are incoherent systems, so there is no really phase information. So it's just you measuring the intensity. So you restrict it with your the antenna size. So for just a general rule of thumb, bigger the antenna, better your resolution is, higher the directivity you have. But radiometers, for example, case of soil moisture active NASA mission operating at the 1.4 gigahertz protected band to sense the ocean salinity and soil moisture over the land, using a 6 meter diameter mesh from space. It's like a big umbrella, open up in space, and looking down to the Earth, and the resolution is about 40 kilometers. The measurement it has is just 40 kilometers because it's far away. Even though the antenna is big, the resolution is small. So what you're measuring is whatever is in that 40 kilometers is contributing. It's a large area.
Yeah.
In addition to that, even though this antenna is big and very directive, but still you have some side lobes and picking up the signals from other part of the Earth as well. So yeah, antennas are usually like a directive antenna you're using it, but it's limited with the physical size usually for a passive, radiometers.
And it's one antenna, right? System most of the time. Most
of the time, one antenna system. Yeah, but there are some interferometric type of antennas as well. But still, if you're doing from a single satellite, still you're limited by the size of the satellites that you can launch. And so usually they have a mesh system so that it's an open up in the space as an umbrella.
Great. Yeah.
I hope I answered your question.
It's great. I'm just thinking if it's possible to use multiple satellite systems, distributed antenna type of systems, and then through some. Now I'm just dreaming right now. Through some coherent processing.
Right.
That's the key. Yeah, get something useful. Yeah.
Right. So the one big challenge is, like, for example, for the radio astronomy, your receiver is on the ground and you're looking up, right? And you have all the storage, resources that you have. You can connect all the satellite, all the ground stations to each other. You can do lots of interferometric processing and improve your resolution. For satellites, those are lacking. So you don't have computational or storage or link to bring down the data at that scale. So it's probably not super effective at this point to have like multiple satellites to increase your aperture size from a passive perspective, because you don't have the phase information, so you just can't do the interferometry.
That's the key. How do you do
if they're not really connected to each other directly.
I don't know how good we're doing or how bad we're doing with time. Nick.
I think given that we started about 10 minutes late, we were going to end around 4:25, which is just 4 minutes from now. But if there is more time needed, that's okay. But depends on if more time is needed. We could do 5 or 10 more minutes.
Okay, so I can share what I have now. These are just my notes. So just because we usually run, it's the NSF mode. We do workshops and take notes. So the talking point so far is or are how to conceptualize and abstract models of sharing, especially with non-comms systems. We're very familiar with comms, or more familiar with comms systems interference, but non-comms is not. It's probably more challenging. Economics aspects of sharing, so it's not always profit motivated in order to formulate or ask the questions, and it's harder to bring a uniform way to study sharing. Need to talk to domain experts to understand sharing, so it's truly cross-disciplinary endeavor. Being aware and to consider advances on the policy side. Sharing brings in trust issues between the various spectrum users. Sharing has space-time dimensions that need to be jointly managed. We need to better understand the closed-loop operations and control. Passive-active theory is a different kind of problem that maybe warrants a bit of more study, because in many kinds of passive, we actually are not always know what we're listening for. So when you formulate things like signal to noise ratio, in this case, we don't really know what the S is. How to reliably do experiments in real conditions outdoors. Passive sensing may have very sensitive requirements, like we've seen from Mehmet's example use case, and small needs to be sometimes pretty tiny sensitivity levels. Experiments are expensive in general, don't scale well in the educational side, and we probably need to explore more focused ways of making below $100 SDRs or low cost in general SDRs for passive active research. So that's what I have so far from this discussion. Oh, sorry. Did I stop sharing? Oh, it looks like I stopped sharing. Sorry. Okay, so any additional points? So one more thing I wanted to mention is I don't know if we have a clear, if we have explored all of the spectrum for the purposes of sharing. So some of the things that, of course, this is something that comes also from the agencies like NTA and FCC. They will every now and then say, okay, we're opening up the spectrum, or maybe we're not opening up the spectrum. So, and there are some spectrum bands that are already shared. There are lots of different entities that are already operating on. And I'm talking beyond like the usual. So people have, I think, yeah, anyway, I mean, I don't want to say too much that it might be taken as asking you to do something or giving up anything. But the point is, you know, beyond the, let's say 6 gigahertz, people are suddenly jumped to work on the beyond 100 gigahertz, which is great. I mean, it's a frontier to be explored, and it probably, I mean, there are fantastic things happening there. I think we'll see a panel later today with different people and previously also working and getting some real results of some practical impact in terms of distances and steering and all of that. So it's happening, and it's offering a lot of opportunity also for doing communication and sensing jointly, which has been also an active area of research for the community. But then actually, I don't think like we have explored quite well still the 20s and the 30s and the 40s and the 50s and so on gigahertz. So so perhaps there's a lot of work to be done there as well. And every time you move by 10, the hardware that exists for experimentation, which is again a wonderful question, becomes suddenly not available, or like, oh, we don't have that part, and your USRP or your whatever platform you're using doesn't quite do it. So it's something to be explored, I think, is like how agile are we in doing our research at different spectrum bands. I think that's also, I'm allowed to add one point, so that's my personal opinion that could be added maybe to the list of points. Yeah, okay.
I'll pick on that too. I mean, there's a lot on the industry side right now, right? A lot of interest in 7 to, what is it, 24 gigahertz, sort of.
Yes. Mm-hmm.
They call it
Yeah.
upper mid-band spectrum.
Yes, right.
You know, for beyond 6G. Which is,
Right. And I think we keep talking about, you know, reaching to collaborators in other domains for spectrum, active and passive, but we sometimes also need to reach to offices, just 2 offices from us in the corridor, and talk to other folks who are looking at maybe the hardware or the software or the interface to maybe have a bit more tools for us to do research. Right? If you team up, if you're more of a networking layer and you team up with someone doing RF front end engineering, you could do a lot of interesting things. And we probably don't reach out, me included, as a faculty. Like, we don't reach out to those other folks very effectively because, you know, yeah. But if we do, we might have more toys to play with and experiment with and teach our students with, as you know, Demetrius pointed out as well, you know. So I mean, there are lots of still spectrum bands that are, I think that are somewhat foreign to us. So okay, 429.
All right. Yeah, I think that's good. Thank you very much, everyone. Thank you.
All right, thanks everyone.
Randy, Demetrius, Kong, Mehmet. Thank you very much. It was a great discussion. And I will probably now pass this on to the next session. Chair Ali.